Okay, um, so last time we covered directional derivatives. I feel like on Friday during class, you guys are probably starting to cover you're going to start talking about local mins and maxes. You're going to be talking about extreme values. Um, so that's what we're going to start doing some examples of today. So I feel like you guys probably understand how directional derivatives work at this point. Alright. So let's say you have a function f of xy, and it's equal to 4 plus x to the third plus y to the third minus 3xy. All right. So now you're going to learn about something called the second derivative test. And that's going to help you be able to classify whether f has a saddle point, a local maximum, or a local minimum at each critical point. So I think rather than kind of explaining what that looks like, I think Weeding probably does a pretty good job of it. I'll just kind of show the process of getting to the answer that you need, and then you'll kind of understand it more when he explains it in class, or if he already has. Good for him. All right, so we start off with the partial of the function in terms of x. The constant goes to 0. You have 3x squared. The y goes to 0. It's constant, and then this is 3y. Then you do the partial y, and then the constant's still 0, x is 0 now. You have 3y squared minus 3x. Okay, so now you're going to do x, the partial of x in terms of x. Again, so that's a 6x, that's a 0. F of y is going to be almost the exact same thing. Just switch variables. Okay, and then to declare its theorem, we know that f of xy is going to be the exact same thing as f of yx, but we could probably just do it anyway. So that's just going to be -3. Oh, that's really terrible, -3. All right. So, -3. And obviously, when you take f of y, and then you differentiate in terms of x, the y goes away, so then you're also left with -3. So because these two are equal to each other, that means that we differentiated correctly, and that means that we can now apply the second derivative test. All right, so what does that mean exactly? Well, let me try and illustrate it. So, So this is what it says. Suppose the second partial derivative of x, derivatives of x are continuous on a disk with center AB. So you got some kind of disk. This is the center. That's at AB. Suppose that f of x AB is going equals 0 and f of y AB also equals 0. So that is a critical point. So essentially in 3D, it kind of does. All right. Imagine that you're looking at a disk, kind of like head on. All right. So something kind of like this. Yeah, that's a disk. And then the function is going to be doing something like this in x, and then function of y kind of goes like that a bit. So it's like forming almost some kind of paraboloid. So it's saying around here, there, at A, B, both f of x, A, B equals 0, also f of y, A, B equals 0. Okay, so that's all well and good, but how do you do that mathematically in order to figure out what those points are? Because all we were given was just this function. Like, we don't have any actual points, so that's what we're going to have to solve for. So the disk that we're looking for is the disk of AB. Because I guess, as you could imagine, these disks get smaller and smaller as they go up to the point AB. So that's the disk, I guess, if you want to look at it that way. It doesn't sound quite right to me when you put it that way, but mathematically, that's really what we're doing. Anyway, the disk at AB, you're going to be taking the partial of x in terms of x, just x differentiated twice. I don't really know how to say that completely, but also multiplied by the partial of y differentiated twice. So those are multiplied, and then you subtract f of x, y at A, B, and it is squared. The reason it's squared is you can determine that because of Clarek's theorem, saying that both xy, partial of xy is equal to f of yx, then these terms don't really need to be multiplied by each other. It just needs to be one that is squared. So if you're pretty confident in your differentiating abilities, and it's like a complicated derivative, that would probably be the best time to check your work. But if you don't want to, then, if you find one and you're confident in it, then just slap that one in there and then square it. Okay, so, all right. Let's try and figure out. So, substituting values in here. We know what f of xx is. So that's just 6x. That's going to be multiplied by the 6y. Subtracting.
-3, which won't depend on AB at all because it's a constant square it. So basically, this is going to, this disk is going to depend on, probably simplify this, just call it 36xy minus 9. Okay. But you're not done? Oh, jeez. Okay. Let's see what else you have to do.
Now it says if D is greater than 0 and f of x at this is good. D greater than 0 and f x also greater at AB greater 0 f a b is a minimum. Okay. I think the best way of looking at that is so like when you're looking at these, like I know it's going to be in your notes, he's going to be showing that, but the way that I was able to figure out why, because it's, I think it's the exact opposite except for the D, yeah, so it's, and f of x, a, b is less than 0, then a b is a max. So if you don't see why this is a thing, you are on the same boat as me. Because like I just had to memorize, you know, like if it's greater than I was thinking like it should be max. And then if it was less than, it should be min, because smaller things, you know, and greater things, you know, max and min. That's the way that I thought about it. But I don't know. It doesn't make sense that way. It's harder to prove it to yourself. So what I remembered it by is like in Calc 1, when you had the test for concavity, like you had the first derivative test, and that just kind of it just kind of proved like the mean value theorem. You had like you could find critical points that way, but if you wanted to know the concavity
of the function, you needed to take the second derivative. So that's essentially what's going on here, because you're just assuming that in both cases the disk is greater than 0. And so now you have your two derivatives, both in terms of x. One is greater than 0. So that means that, all right, let me show you. Yeah, okay. Okay, so I draw it like this, all right? Because in Calc 1, I think when you prove that concavity, when you prove that concavity was positive, that your F double prime was positive, then it was concave up. So the other way was when you proved that it was negative, that it was concave down. So the same works in this way. If it's going to be greater than 0, which means that it's positive, and if it's less than 0, it's negative. Okay, so you can think about that now by drawing the two parabolas. If it's positive, that means that it's going to be an upward facing parabola, because all those values are positive. So then you look at the critical point on a parabola, and right there it is the lowest value of any of these function points, which means that it has to be a local minimum, because you only know this segment of the graph, which means that it's got to be local. It's not like an extreme value, it's not like one of those absolute minimum or maximums, but you do know that it's local, and it has to be a minimum because of what you proved. So same thing, the concavity is negative, you draw the negative parabola, and then obviously no values at this point can be greater. The function values just converge to that one point. Slope somewhere here is going to be 0, so that means that you're going to have a local maximum as well. Okay. So, the reason why my function wasn't working out for the one that we were talking about, it's because I have like this whatever it's called, like a topographical map, but I don't really have a good way of showing you what it does exactly, but the process of what you're gonna do follows exactly what I just did. So it doesn't really matter that we didn't get to an answer. Well, that I can show you at least. But there is still one last thing that you still need to know. Is this isn't just about local maxes and local mins anymore, because now we're in three-dimensional space. So you have the last case in which D is going to be less than 0. This means that the function at point is not a local max or min. However, I believe that that means that it should be a saddle point. Yeah, okay, I got it right, yeah. There is also an interesting case in which, I don't know if he'll ever give you one of these, but our professor did cover it, but I don't think we were ever tested on it just because it's kind of interesting. But if it does equal 0, essentially your test is inconclusive and you have neither proven that it is a local min, a local max, or a saddle point. So, I don't know, that just seems cool that they could actually not work for things. But, alright, so let me see. How I want to show this. I think we all, let me show you the page that I'm looking at right now. All right, so this is obviously some kind of a maximum. This is a minimum. And then this is going to be like one of your saddle points. So you can kind of tell that, like, because the graph, it goes down and like on the sides here, you can see that the slope is negative. Over here, you can tell that these are going in positive direction, goes negative, goes up. So it's like, it's a critical point, but it's something other than a maximum or a minimum, because let me show you kind of what it is. It's a bit like the inflection point on like a x to the third polynomial kind of thing. Because you can see that just at the 0 point, there are two ways. It can either go up or it can go down in slope. And with oh god, I knew what I was doing. Let me just see if I can do it. My point is that it's almost the exact same thing. It's just got more components to it because we're in 3D space. So Bear with me. I'm not sure where those are supposed to connect. Probably just does something like this. So essentially, if you just can see that this slope is going downwards. There's a slope that goes over here that's also going down, but these slopes are going up. Then there is a point that exists in here where both of these, should stop drawing in black. So both these slopes, which we could call like the x direction or something, and both of these slopes, which we could call y, are essentially going to 0 at this point. Like, as this one goes up, it's tracing some form of a parabola, right? At that point, it's going to be 0. Also, at the same time, in this x direction, it's forming a longer parabola, but at the same time, at that point, it's going to 0. So it kind of tricks our test into believing that there is a critical point there. I mean, there is, but it tricks it into thinking that it's a local min or a local max. But the point is that it is neither. So, yeah, if that makes sense, that's good. If not, I'm pretty sure that Weaning will cover more, and he'll do some better Mathematica examples with the graphs there, but I don't really know how to use it as well. So there's that. What else do we need to cover? Yeah, I mean, all these examples are basically just asking if you have three-dimensional software, if you can do it that way. But oh man. Okay, let's try this next one. Okay.
we're gonna approach this the exact same way. Or to find local maximum and minimum values. X, 3x, minus 27, y, and y, negative 27, x, plus. Oh, 3 times 27. Sorry guys, I have to cheat. $81. Actually, that makes a lot of sense. It's just a little early in the morning for me. Alright, 81 y squared. 1. Okay, take it again. 6x, 0, fyy. We're gonna have to multiply 81 by 2. Okay. That goes away, so. I think it should be like 162 then, right? So it's important to make sure that you don't mess up these. So. Can do 3-dimensional calculus, but still struggles with algebraic math. Alright, going back to that and driving in terms of that, it's going to be negative 27. And if you can't see it, I mean, when you do the exact same thing and you say f of yx, the x just goes away and the f of y part 27 comes out. So now you can do your d and ab, which you can now do. Yeah, okay. So if you're noticing a pattern here, regardless of whether this f of xy is a negative or a positive, you're essentially always making sure that these two terms multiplied, evaluated at the point, are greater than 0. Like they're greater than this value. So, so then 29, okay. I mean, because you think about it, if this was a positive value in the xy, it would still be a negative there. So you're always trying to make sure that both your partials
can actually overcome the value at that point. So this is 6x multiplied by 162y. And then that's subtracted from that value. So then I don't really want to do any of these for you because I'm kind of taking from the WebAssign examples. So I don't want to be plugging in and finding VABs. I kind of feel like that's something that you guys need to do, but if you kind of walk through this process enough times, then, VAB will be the easiest part. This partial differentiation stuff is just making sure that you can get to the right answer, So, I don't know. There's only like 6 problems on the website for the locals. Yeah. So, yeah. I don't think I need to show you guys any more examples other than that, because like the only thing that really gets complicated is when they use ease and trig functions. But I feel like you guys kind of know enough about the derivatives on both of those sides that you guys would be able to figure it out. So, yeah, if you guys have, I'm gonna start sending out some more emails so that you guys know to come to these sessions more often. I haven't gotten any feedback from Weaning as to how your test scores were, if the review sessions have been helpful to you guys. But I'm kind of shooting in the dark with all these review sessions because, I mean, I know what all these topics are covering and I got through this class, but I don't know what you guys need help with because you guys aren't here. But I mean, if you're all good A's, good, go ahead. But something tells me that you're not. So that's okay. All right. Yeah, I think I'm done for today. So.